All right, strap in everyone, because today we are going deep, deep into quantum mechanics.
Oh, yeah?
And, specifically how to even begin to understand it.
It's definitely one of those fields that kind of
Yeah.
bends your brain a little bit.
Absolutely. So for this deep dive, we are working with a paper called Understanding QM.pdf
Oh, wait.
by David Ellerman.
Cool.
And in this paper, Ellerman, he really digs into some really complex ideas.
Mm-hmm.
But one of the things we are going to try to pull up for you today
Yeah.
is this idea of objective indefiniteness.
Okay.
Now,
I like it.
that sounds a little intimidating, maybe?
Yeah.
But stick with us.
Yeah.
What it really boils down to is that certain properties of quantum particles don't actually have set values until they are measured. It's kind of like reality itself is
Yeah.
blurry
Interesting.
until we actually take a look at it.
I mean, it's really true.
Right.
Like, if you think about it in our day-to-day world,
Mhm.
we just assume things have definite properties.
Yeah, absolutely.
Like, this table is solid.
Right, exactly.
The quantum world
Yeah.
is much more fluid.
So you were saying it's not even that we don't know the value.
Right.
It's that there is no value
The value doesn't even exist.
until it's measured.
Exactly.
It's wild.
It is pretty wild.
And in this paper, Ellerman really advocates for what's called the literal interpretation
Okay.
of quantum mechanics,
Uh-huh.
which is basically saying, let's not try to explain all this weirdness away
Right.
with classical physics.
Yeah.
Let's just take it at face value.
Totally. And actually, there's a great quote by physicist Abner Shimoni who talked about this.
Okay.
He argued that those indefinite values in quantum states are objectively indefinite.
Okay.
Said,
So it's like a feature, not a bug.
exactly. It's not just that we don't know, it's a fundamental feature of the quantum level.
Wow.
Yeah.
Okay, so how does this objective indefiniteness actually show up in the quantum world?
Well, I think the best example is superposition,
Oh, yeah.
which people describe as,
Being in multiple states at the same time.
right, being in multiple states at once.
It's like Schrodinger's cat, right?
Yeah, like Schrodinger's cat.
It's both alive and dead.
Right.
Until you open that box.
Exactly. Although Ellerman kind of pushes back against this
Oh, really?
common idea
Okay.
of superposition as the addition of waves.
Okay.
Like, you might imagine ripples in a pond.
Right. Okay.
He says it's better to think about it
Yeah.
as a state of indefiniteness
Indefiniteness. Okay.
or indistinctness
Okay.
between different possible states.
So instead of a bunch of separate waves, it's kind of like this
Like a,
blurry mess of possibilities.
yeah, like a jumbled mess.
Okay.
You can't really tell what's what.
Got it. So like a spinning coin?
Yes,
Right.
exactly like a spinning coin before it lands.
Yeah. Heads or tails?
You can't tell.
Who knows?
It's both.
Yeah.
Until it settles.
Okay, I am kind of getting it, but how does this paper actually help us wrap our heads around it?
Well, Ellerman actually uses a really cool trick
Okay.
to make this stuff easier to grasp.
Uh-huh.
He uses a simplified model of quantum mechanics based on sets.
Sets.
Yeah,
Like from math class.
exactly, like the ones from math class.
Wow, okay.
So imagine you have a set like this, A, B, C,
Okay.
and that represents all the possible states a particle could be in.
All right.
And then the set AC,
Okay.
that would represent a superposition where the particle is indefinite
Okay.
between being in state A or state C.
So it's not an A or RC, it's in this...
It's in this weird combination.
Yeah.
Indistinct.
Got it. But how do sets help us see the difference
Right.
between the classical and quantum worlds?
That's where partitions come in.
Partitions.
Yeah, like dividing things up.
Okay.
Think of it like sorting a deck of cards.
Okay.
You could have a partition and that represents a superposition where the state is indefinite between diamonds and hearts.
Okay, so it's showing which states are kind of
Yeah, they're all mixed up.
all mixed up. Yeah.
You don't know which one it is.
Okay.
And he uses this really great analogy to kind of explain the difference between the classical and quantum.
Okay.
He talks about an iceberg.
An iceberg.
Yeah.
Okay.
So imagine the classical world.
Mm-hmm.
That's the tip of the iceberg.
Above the water.
Above the water.
Okay.
Everything's nice and neat,
Yeah.
clearly defined, the
Yeah.
quantum world.
Yeah.
That's the huge part underneath the water,
Okay.
where all the states can be indistinct, all blended together
Wow. Okay.
in these superpositions.
So you're saying that most of reality is actually this hidden, indefinite world?
I know, it's kind of trippy, right?
That is wild.
Kinda,
So
yeah.
how do we get from this blurry quantum world
Right.
to the solid, definite world that we see?
Well, that's where state reduction comes in.
Oh, right, the collapse of the wave function.
Yeah, but
But Ellerman doesn't like to use that term, right?
He doesn't like to use the word measurement
Okay.
because it makes it seem like there has to be a human involved.
Okay.
It can happen without any human intervention.
Got it.
What matters is that there's a distinction made between these superposed states.
So something forces it to
Choose
to choose, yeah.
a single definite state.
Okay, that makes sense.
To explain it, he uses another analogy.
Right.
Imagine you have some pasta dough,
Okay.
and it represents a superposition of all these different shapes,
Mm-hmm.
and you force it through a grater
Okay.
with different shaped holes.
Right.
That represents the distinguishable states,
Okay.
and it takes on the shape of one of those holes.
So it's like popping that quantum bubble.
Exactly.
Okay.
Making it solid.
Got it. And what happens if there's no grater?
That's like a situation in quantum mechanics where no distinction is being made.
Okay.
So the superposition stays intact.
Yep.
And our quantum particle, or dough,
dough.
continues to exist in the state of indefiniteness.
Okay, I like that.
Yeah.
It really makes it clear how important this idea of distinctions is.
It's really central.
Yeah, and speaking of distinctions, the paper also talks about something called Feynman's rule,
Oh, yeah?
which says that the probability of something happening
Uh-huh.
changes depending on whether we can tell which path a particle took.
Exactly. And this connects to the work of John von Neumann,
Okay,
who identified these two fundamental processes in quantum mechanics.
let me guess. One involves making distinctions and the other doesn't.
You got it.
Okay,
He called them type I and type 2.
okay.
Type I is state reduction.
Where you make a distinction.
You make distinctions.
Yeah,
And type 2 is unitary evolution,
and that's where you don't.
where the indistinctness is preserved.
Okay.
It's like letting it be
Yeah,
blurry and undefined.
got it.
So type
Is slicing and dicing?
it's like chopping up that quantum superposition
Yeah.
into something definite.
Got it.
And type 2 is just letting it be
Okay,
this blurry, undefined thing.
I like it.
Yeah.
So to really see how all of this unfolds,
Yeah.
let's look at one of the most famous experiments in physics,
Right?
the double slit experiment.
Classic.
Right.
It's a good one.
It's a classic for a reason.
Absolutely.
It's like the poster child
It is,
for quantum weirdness.
for sure.
So remind me again how this thing works.
Okay, so picture a screen,
Okay.
and it has two slits in it.
Right.
And you fire a beam of particles
Yes.
at the screen.
Like electrons.
Yeah, like electrons.
Okay.
And then behind the screen, you have a detector
Mm.
that records where they land.
Okay.
And here's the crazy part.
Okay.
The pattern on that detector,
Yeah.
it changes
Okay.
depending on whether you are watching each particle
Oh, wow.
go through the slits.
So if you are watching, it acts one way, and if you are not watching, it acts a totally different
Yeah,
way.
it's like it knows.
That is so bizarre.
I know, right?
So how does Ellerman approach this with his set-based model?
Okay, let's stick with our cards
Okay.
instead of getting into all the complex math.
All right, I like it.
So we have got a queen of hearts,
Okay.
a queen of diamonds,
All right.
and a joker.
I am picturing it.
All right, so the two queens,
Yeah.
they represent the two slits.
Okay.
The joker
Yeah.
is our quantum particle.
Okay.
And at the beginning, before it goes through the slits,
Right.
it's in a superposition state,
Okay.
just like our deck of cards.
You don't know which card you're going to draw.
You don't know what you're going to get.
Yeah.
It's all mixed up.
Okay, so the Joker is representing all the possibilities.
Exactly.
Got it.
Now, in
Let's
case
mark.
one of the experiments,
Oh, okay.
we have detectors watching the slits,
All right.
it's like we are forcing the joker to choose.
Hearts or diamonds?
Exactly. As it goes through.
We are making a distinction.
We're making a distinction.
Yeah.
We are collapsing the superposition.
So we are essentially turning the Joker into either the Queen of Hearts or the Queen of Diamonds.
Exactly.
Okay.
And each one has a 50-50 probability.
Just like flipping a coin.
Exactly. It's like flipping a coin.
Okay.
So let's say it chooses to be the queen of hearts.
Okay.
It goes through.
Yeah.
It hits the detector.
It makes a little mark.
Yeah.
Okay.
And if you do this a bunch of times, you will see a pattern
Reflecting that path.
reflecting all the different paths.
Yeah, okay.
Now, what about case 2?
Okay, this is where we don't have the detectors.
So no detectors.
Okay.
So we're not watching the slits.
Yeah.
The joker,
Yeah.
it stays in that indefinite state,
Okay.
a blend of both queens.
Wait, so it's going through both slits at the same time?
Well, it's not really going through in the way that we normally think about it.
Right.
Remember, it's the quantum world. Classical ideas kind of break down here.
Okay.
It's not like a little marble going through one slit or the other.
Got it.
The joker is evolving in this blurry, indefinite state.
Okay.
It's not in one specific spot.
So it's like it's smeared across both slits.
Yeah, like a phantom
A
commit.
phantom card. I like it.
Okay. And here is where it gets really wild.
Okay.
Because it's in this indefinite state.
Yeah.
It creates this really specific pattern on the detector.
What kind of pattern?
It's called an interference pattern.
An interference pattern,
Yeah.
like when waves overlap.
Exactly, like waves overlap.
And you get those like peaks and troughs.
Yeah, but it's not actually waves interfering.
Oh, okay.
It's the objective indefiniteness.
So the Joker's ability to be both queens at the same time.
Exactly. That's what creates this pattern.
So the double slit experiment is showing us that in the quantum world,
Yeah.
particles, they don't follow these nice, neat, classical paths.
Nope.
They are in this blurry world of possibilities until we make a measurement.
Until a distinction is made.
So our intuition about how things work,
Right.
it completely breaks down
Yeah, pretty much.
in the quantum realm.
It does.
Wow. So the particle doesn't actually go through either slit.
It does.
It's just in this indefinite state.
Yeah, until it hits that detector.
That's wild.
It's pretty mind-blowing.
So a lot of physicists have probably struggled with this.
Oh, yeah.
Like, how do we square this?
With our everyday experience.
Right.
I mean, even Anthony Leggett, who won a Nobel Prize,
Okay.
he used to poll his colleagues.
What?
Yeah, he would ask them,
Really?
do you agree that the particle doesn't go through either slit?
And what did they say?
Most of them actually agreed.
Wow. Even though it is so counterintuitive.
Even though it seems crazy,
Yeah.
it just shows you how much we're stuck in our classical way of thinking.
Right. Our brains are wired
Yeah.
for a world of solid objects and, you know.
Yeah, clear-cut paths.
Yeah.
And then quantum mechanics comes along and says, nope.
Right. Throws a wrench in the whole thing.
Exactly. It's like the universe is playing a different game
It really is.
than we thought.
And we are trying to use the wrong rule book.
Yeah, we're trying to use the wrong rules.
So what you were saying is that we need to let go
We did.
of our classical biases
Yeah.
if we really want to get this.
If you really want to understand it.
Yeah, we have to embrace the weirdness.
Embrace the weirdness. All right, I am trying.
It's a journey.
It is a journey.
It is.
So that's what Ellerman is doing in this paper, right?
That's what he's doing.
He is not trying to say that waves don't exist.
Yeah.
But he's saying that they are not the thing.
They're not the fundamental reality.
Yeah. Yeah.
He's saying that the math, it just describes this reality
Right.
of objective indefiniteness.
Okay.
This is just how it is.
So the wave function is not a real physical wave.
Not necessarily.
It's just a description.
It's a mathematical tool.
Right.
A way of representing it. So it's not actually collapsing faster than the speed of light.
No.
Because it's not a real thing.
It's not a physical process
Yeah.
happening in space.
Okay, and this same logic applies to other quantum phenomena, like
Definitely.
entanglement,
Yes.
where two particles are linked.
Yeah. Across vast distances.
And it seems instantaneous.
It does.
But you're saying it's not spooky action at a distance.
Not necessarily.
Just this
It's a reflection of the non-spatial
non-spatial. Okay.
nature of this quantum underworld.
So they're not actually separated.
They're not separated in the way we normally think about it.
Wow.
Yeah, it's a different kind of connection.
So superposition and entanglement,
Mhm.
these hallmarks of quantum mechanics,
Yeah.
they are not in the same space as our classical object.
They belong to this deeper level of reality
Okay.
where those distinctions haven't been made yet.
It's like a hidden dimension
It's like a hidden dimension.
or a realm of pure potentiality.
I like that.
And we're just getting these little glimpses
Through
these bizarre quantum events.
It's like we are looking through a keyhole,
Yeah, that's a good analogy.
trying to understand this whole other world.
And that's why it's been so hard
Right.
to interpret it.
Because we are trying to apply our classical intuitions
Yeah.
to a world that just doesn't work that way.
We are trying to fit a square peg.
In a round hole,
Exactly.
you need a different tool.
Yeah, we need to change our tools.
You need a new tool.
And in this case, the tool is
Accepting
accepted.
the subjective indefiniteness.
That is the tool.
That's the key.
Wow.
It's a big shift.
It is.
But that's what Ellerman is urging us to do.
Let go of our biases.
Let go of those old ways of thinking
Embrace the weirdness.
and embrace the mystery.
Yeah, okay, I am trying.
It's a process.
It's a process. I think I need to reread this paper
Yeah, it's worth a second look.
a few times.
Definitely.
All right, well, this has been
Quite a journey.
an amazing deep dive so far
It has.
into the quantum world.
Oh, sure.
We have talked about Ellerman's argument for taking quantum mechanics literally,
Literally?
with this idea of objective indefiniteness at the core.
At the heart of it.
We have seen how that plays out in the double slit experiment,
Yeah.
superposition,
Entanglement.
all these things we think about with quantum mechanics.
It's all connected.
Yeah.
And, we even touched on how this changes how we think about reality.
Right.
It's more fluid.
It's more participatory.
More participatory than we ever imagined.
Yeah, it is amazing.
It is pretty amazing.
And I feel like we have given our listeners a lot to think about.
I think we have.
So thank you for joining us on this deep dive.
It's been a pleasure.
Into quantum mechanics.
Absolutely.
And until next time, keep those minds curious.
Stay curious.
And those questions flowing.
Definitely.